Okay, let's take a look now at Chapter 4, Section 5, Hamiltonian Circuits and Paths. Yeah, it's not that same Hamilton before. Okay, um, these are named after Sir William Rowan Hamilton, an Irish mathematician and astronomer from, yeah, 200 years ago. Easiest way I know to explain the difference here between Hamiltonian circuits and Euler circuits was if we go back to Königsberg, Euler wanted to walk across every bridge, Hamilton wanted to visit every city. Okay, so Euler paths trace every single line, doesn't matter how many times you hit a vertex. Hamiltonian paths touch every vertex, doesn't matter if you retrace the lines. Okay, so hopefully that makes sense. Suppose you're a city inspector, but instead of inspecting all the streets in an efficient manner, we have to inspect fire hydrants this time. We have the locations there marked on our street network there as the vertex points. And again, the idea here of a Hamiltonian path is we're looking for a route. We're supposed to start at the city garage. Visits each intersection exactly once, returns to the garage. So this could be where you put the video on pause and try and trace that path yourself on your OneNote. So starting with the garage, yeah, don't have to go in alphabetical order. Let's pick one of the ones that are close. Like, all right, let's go to this fire hydrant here and then over here. Maybe we take this nice scenic curvy route here. Back to the garage. That's it. Day's done. Now realize here, I did not trace over, we did not drive down every single street. We're going to go and inspect each of the fire hydrants, and that's it. Okay, we've hit every vertex point. This is a Hamiltonian circuit. Oh, look, there's a hidden message. They've come up with a slightly different sequence than I just showed you. Going from the garage to H, F, around to D, C, A, B, E, J. Well, it's pretty much the mirror image of what I did. You don't have to go over every edge of the graph as long as you're hitting every vertex once. Exactly once. No more, no less. So, what do you think of these? Now, let's also make a distinction here between a Hamiltonian path will touch each vertex in the graph exactly once, but to turn it into a Hamiltonian circuit, this is a path that ends at the starting vertex. Okay? So again, if you want to put the video on pause, I don't want to spoil anything for you here. If I want to start here, I mean, if we want to do the whole, we're starting at a spot, we want to end up at that same place, yeah, we could turn that into a Hamiltonian circuit. So we could turn that Hamiltonian path into a Hamiltonian circuit by just, taking that one extra step. Um, well, the next one, I think that's pretty simple. There, we have a Hamiltonian circuit here. For the third one, Yeah, we're not going to be able to. Maybe I shouldn't start here. Maybe I should start here. See, now that's a Hamiltonian path. I've gone to every single thing, but to get back to where I started, I'm going to violate the basic rule here that we can only go to each vertex point one time and one time only. So maybe that's not a good place to start. Maybe I should start, say, here. We're going to do the same thing again. Now again, we talked about even and odd nodes. Suppose I start here where it's 3, and this one is 3, rather than the ones where it's 2. Oh, that's a bad choice to begin with there. I could complete the... Ooh. That seems a rather efficient way to do it, but again, I don't think for figure C we can turn that into a Hamiltonian circuit. So basically the idea here, trying to put it in numerical terms, if a connected graph, no again, connected, every vertex point is connected to every other vertex point. So for A, that's a connected graph. No, it's not. See, we need another segment going across here and another segment going across here. Um, if it's connected and there are more than two nodes, and each vertex has a degree of at least n divided by 2, then the graph will have a Hamiltonian circuit. So again, suppose we have 4 different nodes where every one has a degree of at least 2, then it will be a Hamiltonian circuit. Okay, again, this is, well, let's go with the odd here. 5 divided by 2 is 2.5. So again, they use this phrase, at least that. So if you have 5 points, the degree of every vertex has to be at least 3, then you're going to have a Hamiltonian circuit. Okay? So then we can extend that to tournaments. Let's take it a step further here. And again, we saw before with the Euler paths and the Euler circuits, sometimes it's a one-way street, so direction matters. We can take a simple tournament here, round robin tournament, I think is what this is showing, where we have 3 teams. Every team plays the other 2. So that means it's a grand total here of only 6 games. Okay. The way we use directionality here is showing who the winner is. Okay. So A beats B, so the arrow goes from A and points to B. Okay, sorry to put it in these terms. Each one of those little arrows there points at the loser. Um, Another game, C beats B, and then the third game, A beats C. Okay, so again, the directions of the arrows there. For every tournament, there's at least one Hamiltonian path. At least one Hamiltonian path. If there's only one that exists, it can be used to rank the teams in order. Let's take a look at an example. Suppose we have 4 teams. playing in the school soccer round robin tournament. Okay, so again, we have 4 teams. Each team is going to play 3 games. Okay. In the first game, it's A versus B. B is the winner. So notice here on our lovely diagram, it goes from B, pointing at A, because A lost. A then plays C, and A is the winner. A then plays D, and D wins. Okay, so looking at just point A, there's 3 different lines there because they played 3 different games. And one of them leads away because basically they only won one out of those 3. In other news, Team B plays Team C, and B was the winner. Now, again, they've chosen, for whatever reason, that's not a straight line. That's all right. B also plays D, and unfortunately, they lost. Okay, so B is 2 wins and 1 loss. And in the final game, C versus D, D wins. Okay, so again, taking a look at the graph there, D has all of the arrows leading away from it. That means D won all 3 games. C, wow, 3 different arrows that end at C. They didn't win a single one. Okay. If we have to follow those arrows, there's only one Hamiltonian path. Don't expect to get this the very first guess. All right, so I don't know, do something silly and start at point A. Well, A only beat one team, that was C, but I have to follow the directions of the arrows. That's a dead end because C didn't win any games at all. There are no directional paths that I can follow from point C. Well, B won a few games. Let's try it from here. From B to A. Again, I don't have a choice there. I've got to go to C. That's not, well, starting at C is obviously a bad choice. All of them end there. You can't follow it. So D has to be my starting point. Now, if I go from D to A, again, I only have one choice. Only one arrow leads away from A. Going to C is a dead end, so I have to go here, and then to A, and then to C. So that's a Hamiltonian path. So B ends up in first place, B is in second place, A is third, and C finishes last. Okay, so hopefully that all makes sense. Again, for an Euler path, we want to trace every single line exactly once. Doesn't matter how many times we cross the same vertex point. For a Hamiltonian path, we want to hit each vertex exactly one time, and the segments don't really matter. We can retrace, we can skip, and again, circuits, you will end up at the same place where you started. So for next time, if you would, again, hopefully open up that digital part of the textbook, or hey, wait, you're home, you could look it up in the actual physical book, page 204, problems 1 through 12, please. And we'll go over any questions that you have during our next Teams meeting.